Okay, we're now going to take a look at one of the most important applications of image formation by refraction, and that is a spherical thin lens. What is that? Well, instead of an infinite side with glass, I have here only a thin piece of glass with both surfaces shaped like part of a sphere. Okay, now imagine I have a beam of light coming in parallel to the optical axis, and here the optical axis is defined as a line connecting the center of this sphere and the center of that sphere. So we call it C2, which is the center of this refractive surface 2, and C1, which is the center of this refractive surface 1. So that's the optical axis. Imagine if a beam of light parallel to the optical axis, okay, pretty close to it too. So I want to know, after getting refracted by both surfaces, where is it going to end up on the optical axis? Okay, there is a derivation in the textbook, and what that derivation did was they used the equation that we obtained for one single refractive surface twice, one on here, one on there. You can follow that derivation easily. What I'm going to do here is something a little different. I'm just going to use, I'm going to ray trace this beam from here to here to here, and directly see where it ends. You'll get the same result. Okay, so please take a look at both methods of derivation. Alright, so here we go. This beam comes in pretty close to the optical axis, which means the angle alpha is pretty small. What's the angle alpha? The angle alpha is the incident angle. The normal line, of course, you know, it's concerned with the normal of this refractive surface 1, so you have to use C1, the center of that first refractive surface. I draw a line. AC1 is the radius R1, okay, the radius R1 of that surface. That angle is alpha, and then after getting refracted, it makes an angle beta with the same normal line. Beta is roughly alpha over n. Actually, in reality, you should see sine beta should be equal to sine alpha over n. This is assuming n equal to 1 here, and this is n, and then go back to n equal to 1 again. So it should be sine beta equals sine alpha over n, but alpha and beta are very small, so we say alpha and beta just roughly, sine beta is just beta, sine alpha is just alpha, so beta is roughly alpha over n. Then it comes into that point B, where it gets refracted again. Okay, the normal line for that refraction, we should start with the optical center of the second refractive surface, which is C2 here. Draw that line here. C2 to point B, that distance is the radius R2 of that surface. Okay, so that angle gamma is the one made between the incident beam and the second refractive surface. After getting refracted, the refraction angle is n times gamma roughly. Okay, n is greater than 1. So eventually it lands here. This is what I call focal point. Okay, all the beams parallel to the optical axis, close to the optical axis, will end up at that point. That is the focal point F. Now what I want to know is how far is that focal point away from the lens. I'm assuming the thickness of the lens between point E and point D is virtually equal to 0. Of course, the way I draw it, it doesn't appear to be so, but that is only for clarification. Otherwise, everything jammed together, we cannot see anything here. Okay, so I'm assuming the distance between E and D is almost equal to 0. In other words, that thickness is far less than the radius R1 and radius R2. Okay, now let's take a look. First of all, this angle is roughly n gamma. What about that angle? I say that angle is roughly n gamma minus theta. Can you see that? Okay, look at the triangle C2, B, and F. Okay, C2, B, and F. The sum of these two angles equals that angle, right? That angle is n gamma, and this angle is theta, so therefore this is n gamma minus theta. Okay, n gamma minus theta. Now, I want to know what F is. Okay, I want to know what F is. And I know that H over F is tangent of n gamma minus theta, which is roughly n gamma minus theta itself. So what I'm going to do now is I'm going to write several expressions down for alpha, beta, gamma, and theta. Okay? And then we're going to then get this F from this relationship of H over F equals n gamma minus theta. Let's see here. Okay. First of all, you can see here, I'm trying to let you see both writings. Okay. Alpha is roughly equal to tangent alpha, which is H over F. Can you see that? H over F. Actually, this is alpha, right? Alpha. This angle is also H over F. Why do I say this is F? Because that distance is virtually equal to 0. Okay? Virtually equal to 0. and that is why you have that. Actually, I should say alpha is roughly equal to sine alpha. I'm sorry, sine alpha, which is h over that length. That length is r1. Okay, h over r1. Now, what about beta? Look at beta here. This is beta, which is alpha over n roughly. Okay. Now, what is let's look at theta here. Theta is roughly equal to sine theta. Sine theta. This is theta. Okay, look at sine theta here. Is roughly h. Sine theta is exactly h over r1. Now you notice that I have called these both h's. Why? Because actually this h is slightly shorter than that h. The reason why I put them the same is because, again, the thickness is virtually equal to 0. So even though this, this line goes downwards, is not exactly parallel to the optical axis, it travels such a short distance that these two h's are roughly equal to each other. Okay, so theta is roughly h over r1. Now, gamma is also very important. What is gamma equal to? Take a look. Look at the triangle ABH. ABH. The sum of these two angles, beta and gamma, should be equal to that angle. But that angle is alpha plus theta. Can you see that? This is alpha, same as this. This is theta, same as that, right? So you get alpha plus theta is equal to beta plus gamma. Okay, therefore gamma equals alpha plus theta minus beta. Okay? And finally, as we said before, h over f is roughly n gamma minus theta. Should be tangent of n gamma minus theta, to be exact. Okay, now we put all of these things together and let's see what we come up with. Okay, let's see what we come up with. Let's see here. N times gamma. What's gamma? Alpha plus theta minus beta. What's alpha? Alpha is h over r1. Right? What is theta? Theta is h over... Wait a minute. H over alpha is h over r1. Theta is h over r2. Right? I'm sorry. From here to there, it's r2. So I should say r2 here. Plus h over r2. Then minus beta. Okay? Minus beta. What is beta? Beta is alpha over n. Alpha itself, again, is h over r1. So it's h over r1 divided by n. Okay? So that takes care of gamma. And then don't forget minus theta. Minus theta. Theta, again, is h over r2. H over r2. Okay, now let's clean this up a little bit. There's h in every term, so I'm going to throw that away. 1 over f is roughly equal to n times, add these terms up, 1 over r1 plus 1 over r2. And then move this term, combine with that. Okay, so minus, what's that? Minus n and n cancels. H is gone, 1 over r1. Minus 1 over r1. Okay, and then what? And then minus 1 over r2. So it's just minus 1 over r1 plus 1 over r2, really. Okay, combine these two terms now. It is n minus 1, 1 over r1 plus 1 over r2. Okay, we now found our expression. 1 over f equals to a good approximation, n minus 1, 1 over r1 plus 1 over r2. This is the same as the expression given in a textbook, the so-called Lensmaker's equation. There's a slight difference. In a textbook, there is a negative sign here, and that's because in our textbook, we define a curve, a spherical curve going this way as positive r, going that way as negative r. But in our case, the way we derive it, both r1 and r2 are actually absolute values. Absolute values. That's why our r2 is considered to be positive. Okay, so if you want to follow the textbook's convention, you use a negative sign here. But remember, since the second surface curves that way, curves to the left, we call that r2 negative. So you end up with the same result. Okay, so that tells you that all beams that are close to the optical axis and parallel to it, after getting refracted by the lens, will end up crossing the optical axis at a point at the distance f behind the lens, and that f is given by this expression, the so-called lens maker's equation, and we'll take advantage of that in many applications. One simple thing you can see here, if n equals 1, that means the lens really isn't there, right? It's just air, right? Then a beam parallel to it, after going through the air, what happens? Nothing. It keeps on going, right? So they will not cross each other until at infinity, which means f should what? Should go to what? Should go to infinity. That's exactly right. When n minus 1 equals 0, you get f equal to infinity, which is right. Okay, and when R1 and R2 are large, okay, so basically they're flat surfaces. If it's a flat surface, it doesn't converge light quickly, and therefore we will find a large f. That's indeed true. When R1 and R2 are both very large, f is also large from this expression. But when at least one of these r's is very small, at least one of these two r's. Okay, let's say R1 is very small. Then one of R1 is very large, which means one of f is very large, which means f is small, which means you're gonna get focused quickly. Okay, that is all quantitatively reasonable. So later on, we'll look at application of this formula, the so-called lens maker's equation, and we can draw ray diagrams for objects placed in front of a spherical lens.